Okay, let's do some Lenz's law problems. We've got this magnet just sitting still right now. We got this loop that's looping in front of this guy's face. It's supposed to be somebody's face who's looking that way, and the loop is going like this. Right now, the magnetic field lines are going out from north and back into south. And remember, they go all the way through the magnet. So what happens if I bring the magnet toward the guy? Well, then, right now, he's got so many field lines coming through the loop. If I get closer, we'll have more field lines coming through the loop. So the direction in which the flux increased, the direction of flux is that way, and flux is increasing in that direction. The direction of the flux increase is the opposite of the induced current. Remember, Faraday's law is d phi dt equals negative EMF. So the direction of the induced current is the opposite of the direction of the increase in flux. So my EMF will create a current that will create a new flux that points that way. So which direction would that be? Thumb in that direction. The fingers would curl around like this. So this guy looking at the loop would see the loop going around like this. That would be clockwise. If the magnet's moving toward him, it would be clockwise. He would see it like this. Now, that's the hard way, figuring out in which direction does the flux increase. A better way to think of it is the induced current. Lenz's law says the induced current tries to stop you from doing what you're doing. Here's a better way to think of it. If I'm bringing the magnet in toward me, I want to stop it from doing that. What kind of magnet would stop this magnet coming in toward me? A magnet that looked like north-south. The induced current tries to stop you from doing what you're doing. So north would face that way, current would flow around. That's the easy way to do these. Okay, what if my magnet is moving away? So now my flux lines are getting smaller because I'm moving away. So even though flux is facing this direction to the right, it's decreasing. That means it's increasing. Flux is increasing to the left. It's decreasing to the right. It's pointing to the right and going down. So it's increasing to the left. Increasing to the left. The induced current, then the EMF, the voltage around this loop, will create a new current that will create a new flux that points in the opposite direction. To make up for that flux, we're losing flux lines. The new current tries to make up for that. Doesn't quite succeed, but it tries. It tries to make flux lines point that way. That's the hard way. The easy way is, how could I stop this magnet from pulling away? Lenz's law says whatever happens here tries to physically stop you from doing what you're doing. Since this magnet's pulling away, I want a south-north to try to attract it back. So that says, remember, thumb points in the direction of north. Fingers curl in the direction of current. My current would flow around like this, or that guy would see it flowing around counterclockwise. The induced current tries to stop you from doing what you're doing. And you can physically feel it. You get this loop of wire and you pull this magnet, you pull it nice and slow, and if it's a strong enough magnet, you can feel it. They're pulling toward each other. It's trying to stop you. Like, you don't get this current flowing around for free. You have to do work to do it. And that work is physically pulling these things apart. Okay, what if I have a south end? Now my magnetic field lines flow like this, flow into south, out of north. And what if I'm moving my magnet toward? Okay, so through this loop, the flux is pointing to the left. And as the magnet gets closer, it's pointing more and more to the left. So we're increasing, the flux is increasing in the left-hand direction, which means the induced current will create a magnetic field that points to the right. Thumb points to the right, fingers curl around. That would be going around like this. So from that guy's point of view, he would see counterclockwise. Again, the easier way to do it is say, well, this guy's trying to come in. I want to stop whatever's happening. Lenz's law says the new induced magnet tries to stop you from doing it. Doesn't succeed, it just tries. What would stop this magnet from coming in? Likes repel. So we'll create a new magnet, a smaller magnet, that looks like this, with south and south together to try to repel this guy coming in. Thumb points in the direction of the magnetic field, direction of north, fingers curl around in the direction of the current. And similarly, if we try to pull the magnet away, field lines are coming through like this, but they're getting smaller because we're moving away. So pointing that way but getting smaller is increasing in that direction. The direction of the flux increase is to the right. So the new magnetic field will point to the left. Again, what's going on is we're losing these flux lines. The new field tries to make up for whatever it is you're losing. If you're gaining stuff, it tries to cancel it out. If you're losing stuff, it tries to make up for it. So we got these new flux lines that will point in the direction. They won't be quite as strong as what you're losing, but they'll try to make up for what you're losing. Or another way to say it, it's like having a new magnet here that tries to stop you from pulling these away. Opposites attract. We want a north over on this left-hand side. Thumb points in the direction of north, fingers curl around. So from that guy's point of view, he would see the current flowing clockwise. Hey, what if my area is increasing? What if I've got magnetic field that points out, and I've got some square loop, say, that's going to be sliding over. So right now, the flux is 0 because he's not in the magnetic field. I'm going to move it in. So after some time, I've got half of the rectangle in the magnetic field. So now, flux is increasing in the upward direction. It went from 0 to being up. So the direction of the flux increase is up. That means the new magnetic field must point down. EMF will create a current that induces a magnetic field that points down. Another way to think of it is we're gaining all these ups. The new guy is going to try to cancel out. Anything you're gaining, we try to cancel out. So that's the old B. These will be the induced B's. Won't quite make up for, I guess I gained 2 there. Maybe I would only make up one of the new I gained. Try to make up or cancel out what you're gaining. Thumb points down. Fingers curl in the direction of I. I would flow around clockwise. Okay, what if I already have my rectangle here in the magnetic field and I try taking it out of the magnetic field? Well, then I'm going to be losing some of these. Now I went from, I had 4 dots. Now I've only got 2 dots. I've lost some stuff, so the new magnetic field tries to make up for what we lost. So I would gain some up magnetic field. So the new induced current would create a magnetic field that points up. So that would flow around counterclockwise. Okay, what if we're changing our angle? Remember, in general, flux in the simplest case is B times A times the cosine of the angle between them. Where by angle between them, we don't mean the angle between B and A. We mean, here's my surface A, it's a flat surface. The perpendicular vector to A, n hat, is the angle we measure, that and B. So if I had B coming in at some angle here, theta here is the angle between B and perpendicularly through A, the normal vector to A. So what if we're changing the angle? Then we'll create a flux. So if I have some constant magnetic field and I've got some loop that I'm allowing to rotate around, so I've got some loop here that's rotating around, where like this, if the loop is perpendicular to the board here, then the magnetic field points straight through it. Cosine of 0 is 1. All the magnetic flux is going perpendicularly through the surface. Our flux is at the maximum. If that's rotating around, now dA, the normal vector, points up, B points perpendicular to that. Cosine of 90 degrees is 0. Now my flux is 0. So I went from maximum flux to 0 flux. That's going to induce a field because my flux is changing. My flux is going that way and decreasing as I rotate. Flux is decreasing in that direction, which means increasing in that direction. The induced field will point in the opposite direction of the increase. The induced field will point that way to make up for these guys I'm losing. They're all pointing that way, and then as I rotate, I'm losing that flux. So the new field will point that way. My current would flow that way. I pointed the wrong way. Point that way. My new field will point that way. My current would flow around this direction. So if I were looking at it from this side over here, that would be clockwise, like this.